Now we are seeing various advancements in abrasive flow finishing process. So in this particular class, we extensively see about rotational abrasive flow finishing process. Why this particular process is important compared to other various advancements and other things we will see. So the overview of today's class, we will see about introduction to various advancements that we have studied in the previous classes. What are those in an introduction way? At the same time, what are the drawbacks of those processes and how one can overcome in this particular process? Need of rotational abrasive flow finishing process compared to other advancements. And we also see the introduction about this one. Then we will see what are the various designs. We do not want to go in deep analysis of the structural analysis and other things, but we just see what is the design 1, what is design 2 and what are the drawbacks of design 1, why we have to go to design 2 and other things we will see. Mechanism of material removal, it is similar to abrasive flow finishing process only, but how the finishing rate improves, that means that material removal rate improves in this particular process. Abrasive paths, if you are giving different rotational speeds, how the path will change, and the finishing of hard tubes also we will see. And initially we will see the flat surfaces, then we will go, initially we will see the flat surfaces, then we move on to the cylindrical surfaces. Then at last we will see what are the surface roughness capabilities, that means that what is the finishing capabilities of this rotational abrasive flow finishing process. And this particular process not only for finishing applications, it can also applicable for texturing and other things. So how this particular process is suitable for or capable of, how this process is capable of producing various textures also. One of the advancement that we have seen is drill bit guided abrasive flow finishing process, wherein the drill bit is placed in between in order to reduce the abrasives to move at the center of the medium slug, that we have seen. And this can be held loosely or it can be held tightly. I mean to say that drill bit can hold tightly in the fixture region. Normally the fixture region is here. So these are the vents are there. Through the vent it will go. So that you can see in the bottom cross sectional view. Only thing is that we are restricting the medium at the center so that the number of active abrasive particles will go on increase. Okay. But the question is, you are restricting here, assume that the drill bit can be rotatable if it is freely there, and because of the medium reciprocation it is rotating and the abrasive particles are getting some random motion and other things. But because of viscous and elastic nature or the liquid nature of the medium, there is a loss from this region to this region. That means this is much gap is there. If you can see here, this much gap is there. This gap, the loss of the medium because of the liquid, so dynamic motion may not be transferred. Okay. But however, the normal motions of this particular process will be there. These are the common motions that are there in the drill bit guided abrasive flow finishing process. One is because of the flute you will get a inclined motion, and because of the reciprocation you will get reciprocating motion. Because of the flute 3D curvature you will get a scooping flow. Okay. This scooping flow along with reciprocating as well as inclined flow, these are all leads to a dynamic motion of abrasive particles at the center of the slug, but it may or may not improve the surface finish or randomize the abrasive particles as we expect, because this is happening at the center of the medium. Okay. But what is our main constraint is the medium has to be activated at the edge or in the finishing region of the workpiece, but here it is not activating at the finishing region. I mean to say the activation should be done on this workpiece, but it is not on the workpiece, but it will improve the finishing rate. What we can infer from this particular process is that the active grains are having certain motion, and this motion is causing some inclination. Okay. At the same time, there are another two advancements. One is the spiral polishing process, where you are giving a rotational motion to the screw, which brings the medium up because of the flutes, and similarly vice versa, so that the finishing action can take place. And in this condition, the medium should be much viscous. If it is too low viscous, what will happen? There is a heavy chance that medium may fall down. But in the condition of centrifugal force assisted abrasive flow finishing process, your medium should be low viscous, because you are going to use, as you have seen, you are going to use a different shapes like circular shape of rod, rectangular shape of rod, square type, triangular type. So many types the author has used, but here if it is too viscous, from the center or from the shape, assume that it is a triangular shape or a rectangular shape. If you want to give some centrifugal motion to the abrasive particle, it cannot reach to the workpiece. Okay. These are some of the drawbacks, but on an average, if you see all these processes, drill bit guided abrasive flow finishing process, spiral polishing process, as well as centrifugal force assisted abrasive flow finishing process, what is the common thing that one can observe is medium or the polymer rheological abrasive medium gets dynamic motion at the center of the medium slug, not at the finishing region. But as a mechanical engineer or as a manufacturing engineer, what I want is, I want to make the dynamics or abrasive particles active in the finishing region. Okay. The medium is viscoelastic in nature. Dynamic motion at the center may reach to the finishing surface, may not reach to the finishing surface. Okay. That is why finishing region will be uncertain about active particles in the finishing region. Okay. So, we will see in particular what are the limitations and modifications that we have to do. The first limitation of this one is improvement of finishing rate in centrifugal force assisted abrasive flow finishing or machining because of the dynamic active abrasive grains. Drill bit guided abrasive flow finishing process gave some idea of the finishing improvement because of the length of abrasive particle motion, that how much distance it is moving. So, because of the inclination, scanning electron microscopy images that you have seen can increase the finishing rate, and due to viscous losses of the medium, dynamic motion which gives at the center of the medium slug may not transfer completely. Okay. This is the basic drawback of almost the three processes that we have just seen the introduction, that is drill bit guided, centrifugal force assisted, as well as spiral polishing. Okay. So, this motion at the central slug cannot give us deterministic micro cross section pattern. That means that the surface pattern that I want, at the same time surface finish also. So, if at all I want a deterministic pattern like a honing process, because in honing process the abrasive particles are fixed on a hone. So, the cross hatch pattern that you are going to get is in a deterministic way. But in this case, if I can rotate the workpiece, what will happen? The motion that you are giving is in the finishing region. For that, what we have done is deterministic finishing direction, improved finishing rate, and desired micro finishing as well as cross hatch pattern. That means the texture can be achieved by giving the motion to the workpiece itself. In the previous condition, the motion is given to the medium, and medium may transfer, may not transfer this dynamic motion to the workpiece because of its viscous losses and elastic losses. Okay. If I can give the dynamic motion to the workpiece, in that circumstances the workpiece will get the cross hatch patterns as well as dynamic motion it can create, and the active abrasive particles will also take part in the finishing process. The version 1, this is the design 1. The basic thing that you can see is we have a motor, and there is a gear reduction system. Multiple gears are there. These are the gears. These gears are connected to a big gear so that the gear reduction can be occurred, and the same rod again we have another gear reduction system, and this will rotate the workpiece parts. Okay. In this way the rotational abrasive flow finishing process is designed, but there is some problem when we designed. This was designed as a part of the PhD program at IIT Kanpur. So there is a problem that if you are rotating at high speeds and if your gear materials are not proper, if you do not have the proper gear reduction ratio, then the teeth will break instantaneously. I mean that after few experiments itself. So if the setup is going bad in few experiments, it will be very difficult to do. So for that purpose, what is the drawback that we have to see? This is a lesson for the master student as well as the PhD students who want to design their setups and other things, because that is how you learn. You have to see what are the drawbacks, what are the things that is going bad, how to overcome it. In this condition, the gear teeth are breaking, and because of which the system is not working properly. Okay. So we do not have anything with the medium and medium reciprocation and other thing, but rotational speed is given because of the gears. Because of this gears breaking, we cannot proceed further. For that purpose, we went on to a new abrasive flow finishing setup where we have given rotational motion. In this one, the new addition is we have taken a gearbox, and gearbox can reduce the speed of the motor enormously. Okay. So if at all I want a 10 rpm, if at all I want a 20 rpm, I can give. In the previous condition, the motor rpms are so high that if you give the gear reduction with respect to gears, it is not possible. Okay. So how it is working in this condition is, you can see here. So the motor, as you know, abrasive flow finishing, this is the lower hydraulic cylinder and upper hydraulic cylinder, and upper medium cylinder and lower medium cylinder. Okay. So these are all things are there, and you reciprocate the medium in the working region. So that's much you have seen in the abrasive flow finishing process. The rotational motion is given by a motor. The motor drives the reduction gearbox. There is a high gear reduction ratio is there, from where these are connected, and from here this is the another gear which is enormously reduced, and this imparts to this particular gear, and this similarly this is connected here, and this is imparted to the workpiece. Okay. That is how the rotational motion is given, and anyhow you have the hydraulic power pack to give the reciprocation motion using the hydraulic energy. Okay. The most important thing compared to abrasive flow finishing process in this particular process is the fixture, how the fixture is designed and other things. If you see here, the gear reduction system is here, gear reduction system. Okay. So that is connected to another gears, and this is the gear that will be a driver gear, and this will be driven to the, and wherein the workpieces are placed. Okay. Wherein the workpieces are placed, and you can see how the workpieces are placed, and moreover most important thing here is that leaking proof, because in the previous setup everything is under the static control, only the rotational motion is given to the workpiece. That is why if there is a static region like medium cylinder and pistons, these are all in static as per the workpiece is concerned, okay, but your workpiece has to be rotated. Whenever you have a workpiece to be rotated, your static system and dynamic system, in between you get a microns gap. In that microns gap, the basic problem is, since you are using a viscoelastic fluid, there will be always chance of leakage. So, in order to prevent the leakage, you should go for some of the things like multiple gear system and O-rings, as well as some of the gaskets and other things we have used, which are not shown here. So, O-rings are used so that it can become leak proof. Then some places we have used the gaskets so that it will completely become a leak proof system. Okay. You can see here the ball bearings are there, gears are there, in between you have the work pieces and the fixtures. So, this is called the complete fixturing system, in which workpieces, and workpiece has its own fixturing system. The schematic diagram also is given here, and the original images is also provided here. This is the fixture, workpiece fixture, and these are the locking plates, locking system or something. These are the work pieces basically that you can place the work pieces. Normally you have provided 4 slots, you can provide 6 slots, depend on your requirement and other thing. As per here, as per this particular design is concerned, we have 4 slots. 4 slots are held by the 4 slotted locking plates and other things, and you can see the dimensions of your workpiece in the schematic diagram. Okay. The most important thing here is, whenever this system is going to patent and other things, the leak proof system, how you make a leak proof system is most important thing in this particular rotational abrasive flow finishing, because most of the system is under static, then only workpiece region is in a dynamic condition. That is why most of the advancements, if you see in the centrifugal force assisted as well as in the spiral polishing and other cases, the medium is given some of the dynamic motions, not the workpiece. Okay. That is why it is somewhat challenge to take, because whenever you rotate a external system, the internal liquid system may also leak. So, you have to make the leak proof. Okay. So, if at all you want to know about how the things are made leak proof and other things, some of the research papers are there, those things you can refer. And forces and velocities in abrasive flow finishing process and rotational abrasive flow finishing process. In abrasive flow finishing process, the forces you have seen already, like you have axial force and radial force and axial velocity. So, this is the radial force and this is the axial force, and you will have a axial velocity, because of which what will happen, you will get the cutting force and cutting velocity. But in the rotational abrasive flow finishing process, the finishing will improve. Why the finishing will improve? Because you are giving a rotational motion. Because of this rotational motion, you have already existing radial force, you have already existing axial force and axial velocity. So, now additionally you are going to get tangential force and tangential velocity, and your finishing force or the cutting forces got additional force and velocity. That is why your finishing action will be much better in this condition compared to abrasive flow finishing process. Hope you understood. If not understood, what is the benefit of rotational abrasive flow finishing process is, in abrasive flow finishing process you have axial force as well as radial force and axial velocity. But in case of rotational abrasive flow finishing process, you have the 3 same, additionally you have tangential force and tangential velocity. That means that you have 3 forces and 2 velocities in a rotational abrasive flow finishing process. Whenever you have another force, extra force and extra velocity, that means that shearing strength of that particular abrasive particle that it is getting from the polymer rheological abrasive medium enormously high compared to abrasive flow finishing process, because of which the shearing action will improve. How the shearing action will improve and other things we will also see in the material removal mechanism of this particular process. And we can see the cutting force. Normally the cutting force is can be taken from the geometry like this, and alpha also we can take from the ratio of velocities, and alpha is the semi crosshatch angle, and the same time Ft is a new thing, that is why it is written tangential force because of the workpiece. Material removal mechanism in abrasive flow finishing process as well as rotational abrasive flow finishing process is similar. Okay. So, how to prove that the material removal mechanism is by shearing and microchip formation and other thing. For this purpose, what we have done is we have stopped the experiment after few number of cycles, like 4-5 cycles or something. I mean to say the reciprocating cycles. Okay. So, you can see this is a grinding mark, this is a big one, this is the grinding mark that you can see here, and the abrasive particles will move in perpendicular direction if you are not going to give any rotational motion. Okay. If you are giving rotational motion also, some of the abrasive particles, I mean to say minimum number, may also travel in a straight line, because this will have the viscous losses and elastic losses and other things. 100% may not listen to the rotational motion, because of which what you can see is some inclination is given here and the chip is formed here. This is called microchip. If you enlarge it, you can clearly see that this portion is sheared and formed a microchip here. The same thing is shown in this particular image also. Okay. So, normally the mechanism, what I mean to say here is, it is shearing action only, and this shearing action is improved because of additional tangential force and tangential velocity, along with the axial force and axial velocity and radial force. But one thing you have noted in the abrasive flow finishing also, I told there is no radial velocity. I mean to say that I cannot say it is 0, but radial velocity is nothing but the indentating velocity that I explained you, that is much less in comparison with axial velocity. That is why we normally neglect it. Okay. Okay. So, you should not note that radial velocity is 0 or something. It is much less, which can be neglected. That is why we always talk about the axial force and axial velocity and radial force only in abrasive flow finishing. In rotational abrasive flow finishing, we add up tangential force and tangential velocity, because of which what will happen, the shearing strength of the abrasive particle or the energy it gains from the medium because of the dynamic motion of the workpiece also will enhance. That is why the shearing action and microchips will improve. You can see here that what is the effect of rotational speed. Okay. If you see, there is theta equal to 0, that means that angle is normally 0 because your rotational speed is 0. Okay. So, whenever you are increasing to 2 rotational speed, now the angle is 22 degrees. If you are increasing to 4, angles go on decreasing. That means that for a height of your cylindrical workpiece where you have placed a workpieces, those length per unit time will increase. Okay. The 19 degrees, then it is go on. If you see here, rotational speed 6, you have 17 degrees, rotational speed 8, you have 14 degrees. At 10 rpm, rotational speed of your workpiece, the angle that you are going to get is 9 degrees. As you increase the rotational speed, what will happen? The angle is coming down, so that means that the length of cutting or the finishing length will improve. Since your reciprocation speed is same, at the same time workpiece is rotating at very high speed, I mean to say not high speed, as compared to 2, if you are using 10, so speed is high compared to 2. In that way, what will happen? The angle is less, that means that it will form a high traverse length. That you can see in this one helical path. If you are see, this helical path is calculated from the scanning electron microscopy images, the surface micrographs that you have seen in the previous slide. So, if we know the workpiece height, okay, that theoretically and at the practically also we can know, because you know the workpiece height and other things, and you know the angle. From that you can calculate what is the experimental helical path length, and helical path also you can generate using this one. So, you can just you need to do some MATLAB programming, which is very simple MATLAB programming, you can do it. And if you put to RPM, it is length is 66.744, slightly increased to 76.8, then 6, then 8, then 10. Normally it is going to approximately 160. Okay. So, that is 160 mm length you can increase. And what I mean to say is, if you are going to increase the workpiece rotational speed, the length per unit time will increase and the finishing rate will improve. Okay. The same thing you can see here. If you are RPM is less, that is blue, only one arc is there, and if you are going to increase, so you can see for a same unit time, the red one is 10 RPM and the pink one is 6 RPM and the green one is 8 RPM and the black one is 4 RPM and the blue one, as you know, it is 2 RPM. Okay. That is there already. So, the helical path length will increase. Why the helical path is coming? Because your workpiece is rotating, at the same time medium is reciprocating. It is resembling like a honing process, but it is not a honing process where you have a fixed sticks are there. Here it is a flexible medium is there. That is why some of the papers they also name it as flexible honing process. Okay. But nowadays there are some other flexible honing processes also available that you have seen in the lectures when I was discussing about the conventional abrasive based polymer finishing processes. Now we move on to the surface roughness or change in surface roughness and material removal in comparison to abrasive flow finishing process in case of rotational abrasive flow finishing process. First we will see the workpiece rotational speed versus change in RA. That means that if your change in RA is increasing, that means that initial minus final, the gap is increasing or the amplitude is increasing. So, you always require the increasing trend. That means that you always need an increasing trend, as you have seen the arrow. So, what is the advantage of this one is, that means that your process is moving in a good direction. But if you see here at 0 RPM, that means that abrasive flow finishing process, what will happen? The change in RA is higher compared to 2 RPM, but after 2 RPM gradually it is increased, 4 RPM it is matching, 6 RPM it is increased. The thing is, at a 2 RPM, that is too low speed, that means that your tangential force and tangential velocity will be much less, or you can say it is nearly minimum. That is why there is no much difference. But why it is reduced, even though it is less, that part I will talk in the next slide. But as you increase the 6 RPM, 8 RPM and 10 RPM, the thing is that it is gradually increasing because your amplitude of tangential force and tangential velocity is increasing, because of which what will happen? Shearing takes place at faster rate and the change in RA will be increased. Similarly, in case of workpiece rotational speed versus material removal also. In material removal, you can see the material removal is increasing gradually as the workpiece rotation increases, because tangential force and tangential velocity come into picture. Though there is very less change in surface roughness in respect to 2 rpm, but material removal is slightly increasing. Now the question is why it is increasing, at the same time why it is not up to the mark when 2 rpm is used. If you see the abrasive flow finishing path, the abrasive flow finishing path will move in a straight line, but whenever you are going to increase the speed or whenever you are giving the workpiece rotational speed, in that circumstances the abrasive particle will follow long distances. Okay. So, because of the long distances, another thing, if you take 2 rpm, okay, and if you see here, you are giving a rotational speed because of which the length of cutting will increase. Okay. That is why if the forces and velocities are low and you have a cutting length is very high, obviously your change in RA will be reduced. That is the main reason why at 2 rpm the change in surface roughness is low. Okay. But if you are go on increasing, obviously the shearing strength will increase because of the abundant amount of tangential force as well as tangential velocity. This is what we have seen about the flat surfaces, but we can now we will move on to the cylindrical surfaces. The cylindrical surfaces, just I will give you the glimpse how the physics works, what is the reasons for the change in RA or the change in roughness, at the same time material removal and other things, for which some of the experimental data is shown here. So, the workpiece is cylindrical hard steel tubes are used, at the same time abrasive particles in are 20 weight percentage, 30 to 60 we have used. Workpiece roughness is increased, the number of cycles also increased from 400 cycles to 800 cycles, and extrusion pressure, that means that how much pressure you are exerting on the medium, that is also enhanced or increased from 4.5 to 6.5. These are all things are given to the experimental data. Now we will see how the surface roughness will improve in case of cylindrical hard steel tubes. Okay. Always looking at the applications and other things may not be good, because many of the PhD students and master students also require some of the experimental data. That is what the intention of us to put the experimental data, how the experiments can be done, also can be understood from this particular slides. At the same time, what is the preliminary experiments, what is the main experiments and other things. You require to do the pilot experiments or preliminary experiments where you can change one parameter at a time, so that you can get the feel what is the trends of the outputs, because output is a function of input. So, input parameter is what you can change, output response you cannot change that. Only thing is that you can feel that or you can get the answer. Okay. So, once you get the feel of the preliminary experimentation, then we move on to the main experimentation. If the material constraint is there, then you can go for some of the design of experimental techniques like CCRD technique, box bracket technique, Taguchi, many things are there. Okay. So, those will give you the complete idea, or if you have enormous material, enormous time and other things, then you can go for full factorial complete experimentation and you can plot, that will be the best one. Okay. So, you have to start with the preliminary experimentation, you should get the trends. Now, you should choose what is the optimum range of input parameters where I can do experiments, then you move on to the main experiments in that input ranges. Okay. So, preliminary experimentation is done, then we found some of the ranges, then we are doing some of the experiments here. And effect of silicon carbide weight percentage, if you go on increase the weight percentage, the gradually the out of roundness is increasing. Out of roundness is nothing but how much it is deviating from a perfect circle. Okay. So, that you can measure using out of roundness measurement. Standard equipments are there, which we have used is Taylor Hobson out of roundness measurement system we have used. And you increase the number of abrasive particles, what will happen? Number of active abrasive particles, that is those are involved in the finishing action, will increase. But if you go on increase, what will happen? The medium viscosity will enormously increase and you cannot add also. At the same time, the problem is these abrasive particles will collide each other and it may become blunt also. But if you see, if the number of active abrasive particles will increase, the material removal obviously will increase in this case. If you increase the rotational speed, because the rotational speed is one of the new things compared to abrasive flow finishing process. In this one, what is happening here is, if you use low RPM, as you have seen, the material removal rate is also less. So, there will be very minimal change in out of roundness. At the same time, if you go on increase, obviously it will increase and it will have such a saturated point beyond which there is no much change in out of roundness. Okay. So, it is, if you increase the rotational speed, what will happen? The finishing length will increase and the interaction frictions are very high. So, the polymer may get heat and other things, because of which viscosity of the fluid may be slightly goes down. Okay. But the machining, if you, that the same thing can be attributed here in the section 1 and section 2. The improvement rate, if you see in the section 1, it is going very fast, but in section 2, because of the viscosity of the medium slightly going because of the heat that is generated in because of the rotational speed of the workpiece. Okay, number of cycles, if you are increasing the number of cycles, the same problem. The medium is constant and you are going for 400 cycles, it is okay, 500, it is okay. Beyond certain limit, if you are going, what is happening here is that the abrasive medium also get the chips inside. So, chips are there along with the medium and abrasive particles. So, obstruction will be there. At the same time, if the number of cycles are more and more, what is the problem is, medium gains the temperature and viscosity will go down. If the viscosity will go down, the abrasive holding ability, what we talk in the grinding process is the grade, will change from hard grade to soft grade. In that circumstances, the abrasive particle will only slide on the surface rather than the finishing. But cumulatively you can see that never the material rate removal can come down, okay, because if you are increasing the number of cycles, obviously the material removal rate may go down, but cumulative value of material removal will go on increase. So, extrusion pressure, if you are going to increase, what will happen is force ratio will increase. So, that what we will see here, if you are going to increase extrusion pressure, that means that the force ratio, that is radial force to axial force, will increase. That means that if you are increasing the extrusion pressure, the elastic component will gain more compared to viscous component, and you can see in the part 1 and part 2. Okay. If you are increasing the radial force, as the literature says that force ratio will increase, this is measured by Professor Gorana and Professor V.K. Jain, that is explained with the experiments that the force ratio is increased and other things. Okay. So, they have used the ring type dynamometer for the workpiece and they have given the extrusion pressure. If the extrusion pressure is increasing, the force ratio is increasing. If the force ratio is increasing, what is happening here? Fr is increasing. That means that your indentation force is increasing. If your indentation force is increasing, then it can create lot of indentations rather than shearings. That is why in the second region, the material removal is less, that means that shearing is less, okay, because of which the out of roundness is less. However, you can see the cumulative material removal will be gradually increased. Out of roundness of the cylindrical tubes, now we will see. So, this is the initial surface where the out of roundness is 3.38 micrometers, and you can see the pen tip image, it is completely blur. How this is done is, we have taken the workpiece, now we have done the partition using a precision saw, and we have checked the for the images. But this cylinder is used previously for the measuring of out of roundness, then only it is made the parts. Okay. So, that one has to understand. In the after finishing, you can see the image of your pen tip and other things are very much clear compared to the previous one, and out of roundness is improved from 3.38 to 1.56, and you can clearly see the out of roundness profiles also compared to the initial one. Okay. That is how you can improve the surface finish, you can improve the out of roundness and other things. So, surface improvement also we have observed in this particular process compared to the abrasive flow finishing process. This is the atomic force microscopical image of the initial surface, that is the workpiece is prepared by the grinding process, and you can see the surface peaks. The initial surface roughness is approximately 900 nanometers in a small area of atomic force microscopy measured area, and after finishing you can see it is improved to 70 nanometers. That means enormous improvement is there. At the same time, you can also see the two dimensional profiles. This is the initial surface and this is the final surface. Okay. This is for long distances. The 2D profiles are for the long distances, and that means that it is for 5 to 10 mm and other things. And in case of atomic force microscopy, you can feel how the surface peaks are sheared off from the workpiece surface, and you can get the nano surface. Okay. So, as I said that the abrasive flow finishing process finishing rate is less. In rotational abrasive flow finishing process, you can improve the surface finishing rate. That means that with the same time the finishing that you can achieve will be better. In abrasive flow finishing process, you will get approximately the same pattern as if you are moving the abrasive particle perpendicular to your grinding surface, then you will get a normal surface. But in a rotational abrasive flow finishing process, you can see the micro scratch direction during the active abrasive particle movement. So, this is while the abrasive particle is moving, that means that your motion of abrasive medium is upwards. Okay. So, the downward motion, this motion, whenever you are pushing down the medium down. So, because of this, what will happen, you will get a cross hatch patterns, that is a honing type of surface you can achieve. So, similar surface that you can also see using atomic force microscopy. This is atomic force microscopy image. Some of the BTech students will be there. So, they should understand that this is the scanning electron microscopy image and this is atomic force microscopy image. Okay. So, in a scanning electron microscopy, you will see the top view and you can see complete surface profile or surface morphology in the atomic force microscopy. Okay. So, here also you can see a part of cross hatch pattern here, and that is most important for the pistons and other cases. That is what the application is shown here. Okay. So, cross hatch patterns can be generated along with the surface finish. That is why this process will be slightly better compared to abrasive flow finishing process. Okay. Summary of this class: what we have done is we have seen the introduction to various advancements, that is spiral polishing process, drill bit guided abrasive flow finishing process, and centrifugal force assisted abrasive flow finishing process are, and then we move on to the rotational abrasive flow finishing process. The need is in the above process. In the above processes, what is the problem is medium is given active motion, which is may not be carried to the workpiece finishing region. That is why we try to rotate the workpiece by having a leak proof system, and then we have designed two designs, and one design has some problem of the gears. So, we move on to the gear reduction system, and we can do the design and development of rotational abrasive flow finishing process. Then mechanism, we have seen how the material removal rate is improved, at the same time finishing rate is improved because of the additional tangential motion and tangential velocity. For additional tangential force and tangential velocity along with the axial force, axial velocity and radial force. And abrasive paths, we have seen the abrasive paths are angular motion is reduced, okay, and this can increase the contact path or the finishing path, so that the finishing rate will be improved. And not only the flat surfaces, we can also finish the hard steel tubes also in this particular process, and we have also seen the surface roughness and texture that is generated. And what we have seen is that it is not only for the application of the surface finishing process, you can also generate the surface textures like crosshatch patterns that are normally used in IC engines. At the same time, you can also improve the out of roundness. Okay. This is the beauty about rotational abrasive flow finishing process, and the advantages of rotational abrasive flow finishing process over the conventional abrasive flow finishing process is it will improve the out of roundness, it will improve the finishing rate, and finishing rate improvement means your production time will reduce. That means that time is money in manufacturing. That is the motive of going to rotational abrasive flow finishing process compared to the abrasive flow finishing process. At the same time, you can also improve the out of roundness. Okay. So, out of roundness may not that much improved in a normal abrasive flow finishing process. Because of the rotational motion, you can improve uniformly at the each and nook and corner of the cylindrical surface. Thank you for your kind attention.